In this video, we're going to talk about how you can quantify a force field by calculating the field strength. This is a little bit different than calculating the actual force field, force that is happening. This field strength is a little bit more generalized. Let's start by reminding ourselves of how we can actually calculate that force in newtons. Let's use this example of the Earth and the Moon and the distance between them to calculate the force of gravity using the universal law of gravitation shown here in the bottom corner. If I plug in all of our values, 6.67 times 10 to the minus 11th. That's my universal gravitational constant, big G, times the mass of the Earth times the mass of the Moon divided by the distance between them squared. You'll notice everything here is in scientific notation, which can sometimes be a pain to plug into a calculator. I strongly recommend using the E notation on your calculator to ensure that you're minimizing your calculator button clicks and also maximizing the likelihood that you're not having an order of operations error that a calculator might do if you're dividing by scientific notation. Remember again, don't forget that squared in the bottom. You will end up getting a whopping force of 2.05 times 10 to the 20th newtons. That is the force of the Earth tugging on the moon, is also the force of the moon tugging on the Earth, resulting in this moon's orbit around the Earth. When we get into circular motion, we will define that a little bit further and calculate the motion of the moon thanks to that force that is acting. So, we are going to talk about today how to calculate the field strength, which is a little bit different than calculating the force. We've already defined how we draw a vector field. These vectors, though, didn't have labels when we were drawing them. They are not actually a force in newtons. They are typically represented as a field strength, which is more generalized. To calculate a force in newtons that the moon was experiencing here, we had to know what the mass of the moon was. When we are talking about a generalized force field, we don't know what the mass of the object is going to be, this test mass or this test charge that we are talking about. So we're going to define this as the field strength. An electric field is going to have a symbol of capital E, whereas gravitational field is a symbol of lowercase g. These fields are technically different things, but we will look at them in parallel because they have a lot of similarities. Now, our units are also very similar. For electric field, it's newtons per coulomb, or NC to the minus 1, and a gravitational field is newtons per kilogram. This is going to allow us to generalize for any object with any mass or any charge in coulombs, and we can then define what the force is going to be for that mystery object. These symbols have some equations that are in the data booklet. You can find E showing up as F over Q. You can also see another equation for E that we'll look at later. And then G has a couple different equations, F over M and big G times M over R squared. Remember little g? We've seen this before. Little g we defined earlier as 9.8 meters per second squared. You used it for free fall, you used it to calculate gravity earlier on. And this is often described as the acceleration of gravity. But that's a very specific case. It's the acceleration of gravity if you're on the surface of the Earth. But little g is more than that. Typically, we are going to now start talking about little g in units of gravitational field strength, which is newtons per kilogram, like we just saw in the last slide. If I expand upon that, newtons is actually kilograms times meters per second squared. Force is equal to mass times acceleration. That's a mass times an acceleration. And my kilograms cancel out, leaving me with just meters per second squared. So newtons per kilogram is actually the same unit as meters per second squared. They just look very different, but they are equivalent. So 9.8 meters per second squared is the same thing as 9.8 newtons per kilogram. We can calculate that. That means that this equation, little g is equal to big G times m over r squared, will help us find the field strength at a given location around a massive object. Um, to know how to plug this in, we are going to look at a couple different features here. We know here that this is the International Space Station orbiting at an altitude of 400 kilometers. This is actually way out of scale. If you were actually to draw that in, it would be closer to here within that tip of the arrow. But that is our distance. That's going to be r. For this mass, we are going to use the mass of the Earth because we are defining the force field around the Earth. We are not going to be looking at the mass of the space station. We are just using that as a location to calculate this field strength. I can plug these values in. There's our big G again, times the mass of the Earth divided by the distance between these converted into meters squared. So 6,770,000 squared. And we get a little G value of 8.73 newtons per kilogram. Notice that that's pretty close to 9.8. It's smaller. Little g is going to decrease the farther you get from Earth's surface. But you'll notice it's not dramatically smaller. Turns out that the field strength at the position of the space station is very similar. Not that much smaller, just 1 Newton per kilogram, smaller than it is at the surface of the Earth. And we can go beyond that. We can look at here's a space shuttle and an astronaut in different locations. And let's say at this location here, G, the field strength is 8 newtons per kilogram. At this location up here, the field strength is 5 newtons per kilogram. Well, we've already seen a way of calculating force of gravity that uses little g. F is equal to uh, mass times gravity. The Fg, force of gravity, is the mass times that gravitational constant. When we used it before, G was 9.8 because that was on the surface of the Earth. But if G can change, we can just change that equation along with it. If I wanted to calculate the force of gravity of this space shuttle, or an astronaut, here let's start with the astronaut, 75 kilograms times 5 would give me a force of gravity of 375 newtons up here. Or if I did the same thing for the space shuttle, 2 million times 5 is 10 million. I can do the same thing down below. 75 times 8 is 600. 2 million times 8 is 16 million. Now, you'll notice here, this allows us to kind of shortcut process of the universal law of gravitation, where you typed in two different masses and big G. Once we have little g, that's most of that equation already. It's everything but the mass of the object. So now we are just taking little g, multiplying by the mass of the object, finish the job, and get a force of gravity. You'll also see here that the astronaut and the space shuttle, they weigh less the farther you get away from the Earth. Now, a common misconception is to understand being in space as fully weightless. There is still a force of gravity, very much so. It's actually not that much different than it is on the surface of the Earth, but we experience it in a different way because there isn't a normal force pushing up. If you are in orbit, you're falling in a different way. Now, there are other ways that we can talk about force field strength. Here's an electric field strength of a particle that has a charge of or 6.3 microcoulombs, experiencing a force of 0.0025 newtons. There's an equation in the data booklet that says E is equal to F over Q. Well, we know a force and we know a charge. We can calculate what E is, just making sure that we're converting things to the right units. So we've got our force of 0.0025 divided by 6.3 times 10 to the minus sixth coulombs. That is converting microcoulombs into coulombs. And we can get a field strength, again in newtons per coulomb, of 397 newtons per coulomb. So sometimes we'll just use that equation given these values to then calculate that piece. There is another equation that can help us calculate the electric field strength, and it has to do with some other things that we'll see later on. The work done moving a charge, magnitude of a charge is our voltage. So we can use this other value that sometimes we'll see later on. It might not make as much sense now, but if we have a pair of parallel plates with a potential difference of 700 volts, uh, V is voltage. That's going to go in for my V here. Separated by a distance of 160 millimeters. What's the electric field strength between the plates? Well, I can just convert that into meters and plug it into my equation, 700 over 0.16, and get 4,375 volts per meter. You'll notice this looks like a different unit than the newtons per coulomb. Um, Turns out, just like we saw with little g, those units are equivalent if you were to look at the base units that are underlying them all. So that is technically the same thing as newtons per coulomb. If we are then asked, okay, that's my field strength, what is the electric force acting on an alpha particle, that's two protons and two neutrons, placed between these charged plates? This one doesn't require a knowledge of voltage. If we were given this as our field strength, we could solve this problem. We know that this alpha particle has no electrons in it. Neutrons don't provide any charge, but protons do. There are two of them, and each one has the charge of 1.6 times 10 to the negative 19. That is the elementary charge. So my total charge on this alpha particle is 3.2 times 10 to the negative 19th. That is going to be Q. I want to find what the force is. I know what E is. So I can rearrange that. The force is E times Q, 4,375 times this charge of 3.2 times 10 to the negative 19th, and I'll get 1.4 times 10 to the negative 15th newtons. So again, this other equation for E could be used given the right values to then find a field strength and then use it later on in another way. All right, the last piece that I want to look at here is what happens if you have multiple massive objects that are impacting the field at a certain location. So let's say we are right in between the Earth and the Moon. Both of them are going to be impacting spacetime, deflecting spacetime, and causing our field strength to change. What we're going to do is we're going to look at each one individually. So the radius, the distance between the Earth and the Moon is 3.8 times 10 to the 8th. Half of that is 1.9 times 10 to the 8th. So that is the distance we are from the Earth. It's also the distance we are from the Moon. I can use this equation for little g to calculate what little g is relative to the Earth, imagining that the Moon isn't there. And the Earth's little g value is going to be 0.00 or 0.11 newtons per kilogram. So now notice we are way farther from the Earth than we were looking at before. That's much smaller than the 9.8 that we saw earlier. We can do the same thing for the Moon. The Moon has a field strength of 0.00013 newtons per kilogram. Same distance, but now we're using the Moon's mass because the Moon is significantly lighter than the Earth. Our field strength is significantly smaller, but this is pointing in the direction of the Moon. So now if we're right in the middle, we're experiencing a little tug of war action where the Earth is tugging on us with greater force field strength than the Moon is tugging on us. And we can just resolve these forces and combine them. Basically, just find the difference of these. 0.011 minus 0.00013 is an overall result of 0.0109 newtons per kilogram pointing towards the Earth. So the Earth definitely wins that battle, but the Moon has decreased it just a little bit, 0.0001 newtons per kilogram worth. Okay, we can extend this and make it a more challenging question. There is theoretically a position that the field strength would be zero. It's not right in the middle. We saw that Earth's field was much, much stronger. So we know that this position must be closer to the Moon than it is to the Earth. If we think of this being a warping of space-time, the Earth and the Moon both distort space-time, and there's like a saddle in between. Since the Earth's gravity well is much larger than the Moon's, that saddle is only going to hit equilibrium at a position closer to the Moon than the Earth. So let's imagine that it's somewhere here-ish. The math here is pretty intense, but what we can do is basically just put a bunch of placeholders. If we know that the radius, the distance of Earth's or Moon's orbit is 3.8 times 10 to the 8th, let's say that this is RE, the distance we are from the Earth, and this is RM, the distance we are from the Moon. Well, um, that means that if we have a net force field strength that's zero, the force from the Moon on this position is the same as or the Earth on the position is the same as the Moon on the position. The only difference here is we're talking about the mass of the Earth, the mass of the Moon, the distance to the Earth, and the distance to the Moon. So we're going to try to make this equation work. Um, if I am looking at all of this, I can take a square root of both of these and cancel out what g is. If I square root everything, it basically gets rid of that square. And I have the square root of the mass of the Earth over Re is equal to the square root of the mass of the Moon over Rm. Now, Rm is just 3.8 times 10 to the 8th minus Re. Those have to add up to this total distance. So that's going to help me minimize one of these unknowns. I'll just plug that in for RM, and I just have RE. Now I have to do some pretty intense cross multiply and do some algebra, and I will end up getting a system that looks like this. You can combine these terms of RE, you'll get this, divide on both sides, and find that the distance you are from the Earth needs to be 3.42 times 10 to the eighth. Of that total, 3.8 times 10 to the eighth. So that is most of the way to the moon, but not all the way to the moon. At this position, the moon's smaller mass, a closer distance, it's going to result in the same force field strength as we see from the Earth. So you can pause this to look at this intense math and see how all of this works out. But all of it is coming from just setting little g equal to each other in each of these scenarios, and then just doing some algebra to make it all work out. So in this video, you should be able to describe how the universal law of gravitation and circular motion can describe the motion of an orbiting body. We will get to the circular motion stuff a little bit later, but understand how universal law of gravitation is part of that orbit. You should be able to describe how and calculate electric and gravitational field strength. Again, this is newtons per kilogram or newtons per coulomb. It is not newtons by itself. It's kind of a placeholder that we can then use to calculate newtons once we know the coulombs or the kilograms later on. And then if you have more than one object, you should be able to calculate a resultant field strength, whether it's gravitational field or you can do the same thing with electric field and just find that resultant and combine those two to get one field strength out of the other side.